Welcome back to Module 3, Fundamentals of Blockchain and Distributed Ledger Technology. In this lecture, we will discuss distributed information systems and information security management principles. In this lecture, we will discuss information system, distributed information system, blockchain as a distributed system, information security, cryptography, and security patterns of blockchain. According to CHAISE learning outcomes, after this lecture, you will be able to explain what is information system, what is distributed information system, blockchain as a distributed information system, as well as the security concepts and the design patterns of blockchains. So, the main learning objectives are distributed information system, to explore blockchain as a distributed system, security and cryptographic patterns of blockchains. So, let us get started. Information system are a group of interrelated components combining hardware, software, database, network, people, and internet to collect, store, and process data to provide information, knowledge, and digital products. Distributed information systems represent an increasingly important trend to computer users that provide a unified system of independent components. They offer resources, reconciliation, and prevent system failure to seamlessly provide service availability to system users. By the nature of distributed information systems, they are high performance compared to traditional centralized systems. They perform distributed transaction processing that fulfills the ACID principles. For example, atomic, the transaction taking place must be indivisible for the others. Consistency, the transaction should be consistent after the transaction has been done. Isolated, a transaction must not interfere with another transaction. Durable, once an engaged transaction, the changes are permanent. Transactions are often constructed as several sub-transactions jointly forming a nested transaction. So, distributed information systems are more resilient and self-fault tolerant due to the distribution of resources and operations. For instance, if some nodes are down, the system will keep functioning correctly because other nodes are up. Characteristics of distributed information systems are defined as a distributed information system is more powerful than typical centralized systems due to the combined characteristics. For example, resource sharing, where each resource requires its management policies and methods. It brings openness and how it can be extended. Concurrency, multiprocessing, for example, parallel executions in distributed systems, and scalability are the core characteristics that play an important role in the acceptability of distributed information systems. As previously stated, such systems are fault tolerant due to hardware redundancy and software recovery. Moreover, they bring transparency to the data and transaction process. Security plays an important role in the current era of internet. From the perspective of software systems, security is to protect software services and data from intentional harm, to keep functioning the organization's operations, and to enable software to continue function correctly against other malicious attacks or attackers. So, the one thing to notice here, there is no 100% security. You can achieve some level of security that satisfy the stakeholders or the system stakeholders. Information security protects the data from data and information within the system from malicious attackers against unauthorized access, disclosure, modification, or we can say like data tampering or resource tampering and information tampering, inspection. For example, like there's two different parties who are communicating with each other, and the attacker come in between them, and then they start inspecting the communication and the information or the data which is flowing between two communicating participants. Information security enables CI triad, which belongs to confidentiality, integrity, and availability of data within the software systems. And this CI triad model guides policies for information security within software systems. Is security matter in software systems, or why security is important? For example, when we speak about security, we are speaking about the data confidentiality, integrity, and availability, and to protect overall system from the attackers and malicious users. So when enabling security in software systems, it protects confidential data, enables secure operations and communication between different parties, and protects against malicious attackers that harm the system for their personal gains. For example, the attackers can steal information, monitor the content which is sensitive or which is confidential between two different parties, and explore different vulnerabilities to exploit them and to get control over the system for doing or making more damages to the system, or for the future usage like sniffing the information or collecting the information by sitting in the system by introducing some malwares or viruses. This such acts compromises the confidentiality, integrity, and availability of the system. So not taking the proper security measures and controls makes software systems insecure and vulnerable. For example, like I have spoken about the malwares. So the malwares within the software systems can cause denial of services attacks or crash the systems. They can disrupt the services of the system. So the organization cannot perform several services. They cannot satisfy the consumer needs, which leads to business closure, reputation loss, or negation of the trust of the organization. So if one organization cannot provide their promised services, the users will stop using their services, as well as they can lose the reputation in the market. So other competitors can get more customers if they will lose their customers just because of the security attacks. Similarly, weak security controls on the database can lead to customers' sensitive data modification risk, and organization can face heavy sanctions and fines, for example, like GDPR compliance issues or HIPAA compliance issues. So the organizations should have to maintain the confidentiality, integrity, and availability of the user's data within their systems. Blockchain as a distributed information system. The first and most important aspect of blockchain is that it runs over a peer-to-peer network, that is a distributed network of untrusted participant nodes. Each participant node holds an identical copy of the ledger. A ledger, a shared ledger that each participant node holds, and when a new transaction or block creates, it replicates over the participant nodes. So blockchain manages to achieve CAP theorem, or it satisfies the CAP theorem, which belongs to consistency, availability, and partition, where the consistency in terms of eventual consistency over time through consensus. So the eventual consistency we can satisfy by using the consensus mechanisms which blockchain uses. For example, like proof of work, proof of stake, delegated proof of stake, or practical Byzantine fault tolerance consensus algorithm. Based on the CAP theorem, blockchain as a distributed system brings consistency where distributed ledgers keep immutable digital records and a single latest copy of data that is shared among all the network nodes. Also, it provides resources and services available to users while keeping a system up and accessible by accepting a large number of requests and responding without failures, and thanks to the distributed nodes in the blockchain networks. Partition enables the self-fault tolerant. For example, the system continues to operate even if a group of nodes fails. For instance, if in the case of denial of service attack, this denial of service attack can make down several nodes on the blockchain network down, or to stop their participation in the blockchain network. It may hurt somehow to the blockchain, but it will not diminish, or it will not stop the services of blockchain network, because other participant nodes all over the world are participating in the system. And this belongs, this concept belongs to how big is the blockchain network. If there are more number of nodes, it means it is more difficult for the attacker to down the blockchain services or blockchain based application services. So, blockchain before Bitcoin. So, what was before Bitcoin? For instance, like we are discussing, like Bitcoin emerged in 2008 with Satoshi Nakamoto paper, and then in 2009 he brought the concept of Bitcoin. So, what was before blockchain? What type of components existed already which Satoshi Nakamoto used and combined together to brought the Bitcoin cryptocurrency, which later emerged or which later brought the concept of blockchain technology. So, Bitcoin is built on earlier works. For example, like Bitcoin constitutes distributed computing, peer-to-peer network, cryptography and Merkle tree. All these concepts were existed before the Bitcoin implementation or before the Bitcoin, as well as the cryptographically linked blocks presented as by Stuart Haber and Scott, invented in 1991, and smart contract idea brought by Nick Szabo in 1997. Smart contract, which of course, like we have discussed, is a piece of code and execute automatically within blockchain network. So, the Nick introduced the digital currency BitGold in 2005. However, it was not a successful project because there were various challenges in the digital currency. So, the question is here, what difference Satoshi Nakamoto did in the Bitcoin that became its a successful cryptocurrency as compared to the BitGold of Nick? So, I will say here, like pause this video for 2 minutes and think about what type of concepts Satoshi Nakamoto used within Bitcoin to solve the BitGold issues. I hope you have already find the answers, and your answers is similar to this. For instance, Satoshi Nakamoto solved the centralization and double spending issues in digital currency. For example, proof of work that uses mining to solve cryptographic puzzles and agrees on the ledger's true state. Also, the concept of confirmations, block confirmations, to protect against malicious changes aiming to double spend digital money. Moreover, he introduced the incentive layer combining cryptoeconomics to keep nodes honest over the network. So, the nodes which are participating in the network, they will stay honest, they will perform their operations we can say like in a legit manners, and they are not corrupting the system, they are not introducing any vulnerabilities, or they are not performing any invalid operations. And by this crypto economics or incentive layer, they are getting rewards in the terms of mining rewards or transaction fee rewards. So, the consensus, the core concept, the concepts which Satoshi Nakamoto used as in the context of using proof of work. So, blockchain uses a decentralized consensus mechanism to maintain the state and immutability of the ledger. Consensus adds a new block once miners solve the cryptographic puzzle, create a fault tolerant environment, and solve a double spending problem in digital currency. As we discussed previously, Bitcoin uses proof of work consensus. Proof of work is a computationally rich, energy-waste consensus strategy where special nodes called miners define the state of the ledger by solving complex cryptographic puzzles by using specialized crypto mining machines. In contrast, there is another consensus mechanism which is called proof of stake. It does not follows mining, but their miners becomes validators, and they lock some cryptocurrencies in their wallets to participate in the consensus mechanism. So these consensus mechanisms are fault tolerant and achieve mutual agreement on a single state of the distributed ledger. Once consensus is reached between the nodes for a particular block or its transaction, they terminate the consensus and send a block to the blockchain for propagating or for distributing or sharing to other participant nodes on the blockchain network. So we were discussing about proof of work. So I will just give briefly a quick overview of proof of work consensus. So proof of work consensus requires a huge amount of energy to run or to solve cryptographic puzzles by running specialized crypto mining machines which run some algorithms or some process to solve the provided cryptographic puzzles to find the next block. So it is one of the first decentralized consensus mechanism used in the cryptocurrency Bitcoin. And using mining equipment machines, miners solve cryptographic puzzles to earn incentives in terms of cryptocurrency. For example, like in the Bitcoin, once they find a block, they get a block reward, which is currently at 12.5 Bitcoins, if I am not wrong, and it get half after every 4 years. So it means after 4 years or after some time, they will get half to 6.25 and then later 3.125, and it will keep reducing after every 4 years. But once Bitcoin rewards were started, there was like at that time 50 Bitcoins, later they become 25, and then they start getting reducing and reducing after every 4 years. Confirmations. This is a very important concept within blockchain to handle the double spend issues. So this block confirmations concept which Satoshi Nakamoto brought, this solves the double spending issues not only in Bitcoin but all other cryptocurrencies which exist. So for instance, during the BitGold time, once the transaction is happened, anybody can perform the transaction immediately to the transacted amount. So there was chances of spending the same coin or same transaction twice. So this concept or this problem was existed in all the digital currencies before Bitcoin. So now the Satoshi Nakamoto introduced the block confirmation. So blocks which should be appended before making the transaction final, or to bring the transaction finality to spend that transaction again, there is a requirement of appending some blocks. For instance, like each block that is added on top of the previous block, previous valid block, it contains as like a confirmation. For example, if my transaction is included in block 100 and the block chain is like 103 blocks long, it means my transaction has 3 confirmations. The more the confirmation, more blockchain is secure. So I have one very simple and small task for you. Just imagine if your transaction was added in block 700 and currently the blockchain is at 725 blocks long. How many confirmations your transactions received? I hope you have already found your answers, because it is just like a mathematical equation. So solving it like 700 minus 725, so is a 700 almost like 25 blocks long. So you have like 25 confirmations. In the previous lecture, many times we were speaking about consensus and validator nodes or validation process. So the concept of consensus and validation both is different, but they perform on the similar stage. So blockchain validator is someone who is responsible for verifying a transaction within a blockchain network. For example, when a new transaction occurs, validator nodes perform a series of checks to make sure that the transaction is valid. Validator nodes validate the sender has a balance before they add the transaction to a block. They check the transaction is legit. For example, like they check the signature of a transaction. If it is invalid, then the validator will ignore or discard the transaction. If the signature is valid, then they will let it further for further processing. So, to not they also check the transaction which is created, it is not double spent. For example, like the transaction is not already consumed. Here it is important to note that validation and consensus are not the same thing. The blockchain validation process precedes the consensus process. It means the transaction validation happens on each participant node, and the validated transactions are stored in the mempool, which we call like memory pool of each participant node until they are confirmed in a block. Cryptoeconomics is an economic interaction mechanism in adversarial environments. For example, like encouraging nodes to stay honest. So, according to Ethereum developer, the protection or the protocols govern this cryptoeconomics or incentive layer protocols govern the production, distribution and consumption of services in a decentralized digital economy. In incentive layers, the cryptoeconomics terms is heavily used. For example, like we previously discussed cryptoeconomics as well. So, cryptoeconomics is an interesting concept within the blockchain itself. It enables a combination of cryptography and economics, also known as like game theory. So, cryptoeconomics enables the feature that funds who benefit or protect the blockchain network. For example, like data validators, miners and full nodes, they are participating in the network and also they are benefiting the blockchain network overall. Like they are keeping they are performing the minings, they are keeping the ledger, they are protecting against the data tampering or other attacks. So, by performing these operations, they are getting some rewards as well in the terms of like mining rewards or transaction fee rewards. There are punishments as well in the cryptoeconomics who hurt the blockchain network. For example, like there are malicious attackers or we can say like malicious users or nodes that joined the network only in terms to hurt the system, to block the operations of the blockchain network. For example, either they are performing denial of service attacks, either they are introducing some modifications in the transaction or in the block to invalidate the ledger. So, all such malicious activities or malicious operations performing by malicious users or attackers, the system can identify and then he can punish, then the system can punish those nodes. For example, like if they are participating in proof of stake consensus mechanism, then all their staked crypto assets will be taken, and if they are getting some mining incentives in the case of like running proof of work, then their mining incentives will be taken back. And also in the future the system or the network will block them for participating in the network. In this process, miners in general we can say like in cryptoeconomics in the terms of like in a proof of work concept, miners solve the cryptographic puzzle and create the next block, and by doing that they are receiving the reward incentive. So, this is like a simple term, or we can define what is like incentive layer over the cryptocurrencies or the digital currencies which are currently operating. So, now we are moving towards security and cryptography. So, what type of security concepts or cryptographic techniques or components blockchain is using, or why blockchain is considered as one of the secure technology. However, it has like different security threats and different security attacks or risks, but still it is considered as less vulnerable as compared to the centralized systems. But how? So, what are the components? Why it's making it less vulnerable or more secure as compared to the centralized environment, centralized system? So, one of the answers is that cryptography, because cryptography is an integral part of the blockchain network, and cryptography helps to validate transactions integrity. Cryptography is also involved when generating crypto puzzle that miners try to solve when reaching a consensus. The incorporation of cryptography in blockchain protects against various attacks and risks. For example, like sensitive information leakage, privacy protection, data modifications, denial of services, man in the middle. So, the list like goes on. Cryptography plays a role to make blockchain or the concepts which are used within blockchain secure. For example, like wallets that hold crypto assets and keys. So, the cryptography is involved in this in the crypto wallets. So, like generating private and public keys and the addresses of cryptocurrencies as well. Once we are performing the transaction, it also involves the cryptography. For example, like it keeps the information about like sender, receiver, amount and other necessary details, as well as it keeps the transaction some cryptographic signature within the transaction to verify, to validate the transaction which is performed. It is coming from the right person, it is not double spent, and it is going to this particular address. The cryptography also introduced the security in the concept of like protecting data against malicious attackers, like from like modification or sniffing or just like collecting the data. And also it helps to preserve the privacy, because blockchains are pseudonymous in terms of blockchain transactions are not related to the user's identifiable information like emails, identity or other identity informations, but they are related to the cryptographic addresses. So, the cryptographic addresses which belongs to the users who is performing the transactions, nobody can identify by looking those addresses, like who is behind this transaction. So, there is like some sort of like privacy which is providing by the blockchain using cryptography. Blockchain includes various cryptographic based mechanisms. For example, like it brought the concept of like public key cryptography, like asymmetric cryptography, hashing mechanism they are using, and they are using Merkle trees, which is a hierarchical tree like structure, and they are using zero knowledge proofs, and of course like zero knowledge proofs are used by different cryptocurrencies as well. So, these zero knowledge proofs are like proving the transaction without knowing like who is performing the transaction, or without completely know about the knowledge of that particular transaction. However, this zero knowledge proofs has to fulfill three different characteristics, like the completeness, soundness and zero knowledge, and these concepts we will discuss further in detail in the upcoming lectures as well. So, what is public key cryptography in blockchain? So, blockchain incorporates traditional asymmetric cryptography that uses a pair of keys, for example, like public and private keys. Public keys can be shared with anyone, and it is publicly available. For instance, like you can send to your friend or someone else who is performing the transaction for you. Each public key has a corresponding private key as well, and the sender uses the key to encrypt the information, and the encrypted information is securely sent to someone who owns the corresponding private key. For instance, like you signed some transaction by while using my public key, and then you can send that transaction to me, and then I will verify by my private key, which I hold only to myself. So, here is an example, like for example, like the encrypted information can only be accessible that possesses the corresponding private key. For example, myself, if I have like private key, I can encrypt the information, I can read the encrypted information. As compared to the public key, a private key is like a password, and the recipient uses this key to decrypt encrypted information from the sender. Private keys provide ownership to assets within the wallet, and it's used for transaction signing. So these are the like different operations or the actions which we can perform by using public key cryptography in blockchain. So public key cryptography has a very rich role in blockchain. For example, like when a user creates a wallet on a blockchain, they are generating a public private key. Also in blockchain, public key cryptography is used to create wallet address. And wallet address is just like a string of numbers and letters generated from public key, and it is public to everyone and used to check the balance in the respective wallet if it is attached to some cryptocurrency. The wallet address receives coins or cryptocurrencies. The wallet addresses holds crypto assets and sends coins from the wallet when the private key proves ownership. Transaction requires a signature from the private key of the sending wallet. Typically, a transaction represents like take X amount of assets from my wallet to credit X amounts of asset into another wallet. So the wallet's public key ensures the authenticity of the digital signature of the private key. This is one of the role of block validators when adding any transactions to the blockchain. And once it is confirmed, like it is a valid transaction, then the transaction is written into the ledger and the balances are updated. Hashing in blockchain. So the cryptographic hashes are fixed in length. For example, like hashing functions requires an input string of any length that produces a fixed length output. Does not matter like if the input is 1 or 100 characters long. Hashes are also deterministic, which means it does not matter how many times you give the function a specific input, it will always have the same output. The cryptographic hashing function generates an irreversible one-way hash, and it is impossible to determine an input from the output of the function. So, for example, like you give like one word to and to hash that word, you cannot bring that word back from the hash. So, they are like one way, they are irreversible. Cryptographic hashes are collision resistant, and no two inputs can ever have the same output. For example, like if there is a letter A and you are using a hash algorithm on that, it will produce different hash string as compared to the hash of letter B. So, you can see like there is only a one letter difference A, B, but their hashes will not match. Moreover, hashes are used to perform quick computation and verify the authenticity of the data. Sorry. Cryptographic hashing also has a centric role in the blockchain. For example, in a blockchain, every new block of data contains a hash output of all the data in the previous block. A cryptographic hash connects every next block to the previous unique hash. Even one bit of data changes in a block would alter the hash output of all the previous blocks, and this would invalidate the entire ledger. Hashes provide tamper evidence. Different blockchain platforms use different hashing mechanisms. For example, Bitcoin uses a cryptographic hash function called SHA-256. Ethereum uses KECHEK-256. The main purpose of cryptographic hash functions is to utilize for security and mining in the blockchain. Merkle trees in blockchain. Merkle trees are hierarchical tree-like structure that represent parent-child node relationship. Groups of nodes within the tree are called subtrees, and a node with no children is called a leaf node. A Merkle tree utilizes the cryptographic hash functions to store the hash outputs instead of raw data in each node. Merkle root is we can say like is simply the root or top node of a Merkle tree, meaning it represents a hash output of the combined hashes of the left and right subtrees. So, Merkle trees in blockchain organizes transactions in a block and verify the integrity of the transaction. So, once we were speaking about in the previous lecture, once we were speaking about the block header and the block body. In the block body, we discussed like the block body contains the Merkle tree where the transactions are stored in the form of Merkle tree. So, the Merkle trees in blockchain organizes transactions and they check the transaction in a given block have been tampered or not. For instance, like in for example, like if someone want to verify this transaction is legit or not, or it is authentic, or it is not tampered, then system can check while traversing only the Merkle trees from that particular block. Merkle tree also helps to trace the specific transaction that is being tampered with. For example, like let's say like some attack happened on a blockchain network and some malicious attacker was successfully tampered one block. So, in that case, once the blockchain validation stage is going to happen, or the full nodes are going to check the blockchain, and then the system can identify which ledger or which particular block in the ledger is tampered. So, in that case, the all other participant nodes can discard that corrupted ledger, corrupted block from the blockchain, and then they can start using the correct one. And in this process, Merkle trees can help to traverse and trace that particular transaction. Merkle trees allows users to verify that their transaction has been included in a block without downloading the entire blockchain, and it makes a transaction traversal very easy within the blockchain. Zero knowledge proofs means that person A can prove to person B that he knows a certain piece of information without specifically telling him that the knowledge is what the knowledge is. So, zero knowledge proof satisfies the following requirements or following parameters. For instance, like completeness. Completeness is like if the statement is true, then an honest verifier can be convinced of it by an honest prover. Soundness, for example, if the prover is dishonest, they cannot convince the verifier of the soundness of the statement by lying. A zero knowledge, for example, if the statement is true, the verifier will have no idea with the statement or what is the statement actually is. So, zero knowledge proof mechanism come with or we can say like zero knowledge proof mechanisms comes into play when different operations are performed within the blockchain. For example, like end-to-end encryption when performing the transactions, and for instance, like zero knowledge proofs to maintain the transactions integrity and privacy. For authentication, by not reveal the inner workings of the entire transaction and allows the system to maintain abstraction, which of course like it makes infinitely easier to use. Zero knowledge proofs within blockchain networks ensures storage protection. For example, like it safeguard the storage units, and it enables sending private blockchain transactions in order to keep transactions out of the reach of third parties. For instance, like there are several cryptocurrencies or blockchain platforms which are using zero knowledge proofs just for these concepts, like to keep their transactions private which are not readable from the third parties. For example, like Zcash is a cryptocurrency which was once a very familiar cryptocurrency, because they brought this concept first time using zero knowledge proofs to hide their transactions from third parties in the permissionless environment. So this is the concept like which is of course like still in the use, and a lot of blockchain networks and platforms are using zero knowledge proofs just because it has very sound and valid reasons while performing the transactions in the blockchain network. There are some security patterns. In previously we discussed some design patterns, so there are some security patterns as well which should be implemented or which should exist within the blockchain application or within the blockchain networks to help to secure or to further secure the blockchain applications. For example, like security patterns within blockchain concern the security of blockchain based applications. The security pattern is related to multiple authorizations, where multi-signature mechanisms are used to authorize transactions along with the binding of authorities. Off-chain secret enabled dynamic authorization, for example, like escrow claims between different parties. X confirmation technique we have already discussed. So this X confirmation technique is to wait for a certain number of blocks to protect transactions against double spending. For example, like we were discussing, like Bitcoin uses 6 confirmations once the transaction reached to its finality, and then you can spend that transaction again. So this is one of the security pattern within the blockchain. So for instance, like there are there are different security threats which are related to not having enough block confirmations. For example, like there is zero confirmation attack, there is FINE attack, there is one confirmation attack. So these type of confirmations attacks happen in the fast networks, where the retailers or their different companies accept the transaction without requiring any confirmations from the network. So for example, like if you're going to buy a coffee from some shop, and they can say like, okay, I'm paying by Bitcoin, and then this coffee shop will accept your transaction just after performing the transaction without requiring any confirmations. So meanwhile, you can trigger another conflicting transaction within the network, and then you can perform this double spending of the same spent Bitcoin. So this is like one of the case where X confirmations are required to bring the security within the blockchain network to protect the ledger from getting invalidate or introducing or letting attackers to introduce the double spending within the blockchain networks. So in summary, in this lecture we discussed information systems, what are distributed information systems, and we learned about blockchain as a distributed information system and what type of characteristics blockchain hold that is making it like disrupting in different applications domains, or making it emerging or usable in the context of decentralized applications in supply chain, healthcare, finance, Internet of Things, or introducing it as a security layer. Blockchain is using different security aspects. For instance, like how to make the blockchain network itself secure. So they are bringing the concept of using like consensus mechanisms, for instance, like the proof of work, as well as the validation or the nodes which are participating in the networks. They have different roles. For example, like we discussed, like validator nodes, they perform like validations, which is precedes the consensus process, and this validation process helps to check the transaction is not double spent, the transaction is coming from a legit user and it is going to a legit user as well, and how much amount it holds and every other details which need to be fulfilled for a single transaction. And then we discuss the cryptoeconomics concept, and in this concept we discuss like Satoshi Nakamoto brought the concept of incentive layer to help to overcome the issue of double spending in digital cryptocurrencies. For example, like Nick introduced BitGold, which has all these issues of like double spending. It was not decentralized, it was like managing by some particular authorities. So all those issues which was particularly relevant to BitGold cryptocurrency were solved by Satoshi Nakamoto by introducing consensus mechanism and incentive layers by introducing the cryptoeconomics technique. Later we discussed blockchain, cryptography role in blockchain, as well as we discussed some security patterns. And in cryptography role we discussed public key cryptography and how and what type of roles it is playing in blockchain, for example, like creating cryptographic wallets, addresses, and as well as signing transaction and verifying the authenticity of the transaction. We also explored hash algorithms which are used within blockchains. For instance, like Bitcoin uses SHA-256 and Ethereum is using KCheck-256. Both hashing algorithms are deterministic and irreversible. And similarly, other hashing algorithms are also deterministic and irreversible because these are the core characteristics of hashing mechanisms. And we also discussed Merkle trees and how the transactions are organized in the Merkle trees within the blockchain and one particular block which where, for instance, like the transactions are listed as like a binary tree, and then they are organized in the block body. And then we discuss the zero knowledge proofs, which brings the concept or which brings the parameters to fulfill, for example, like soundness, completeness, and zero knowledge. And different blockchain networks are using these zero knowledge proofs, for example, like Zcash we discussed. So after this lecture, now you are more confident to explain the terms related to information systems, distributed information systems, blockchain as a distributed information system, different security aspects of blockchain, and the role of cryptography in blockchain.